Okay, welcome everybody to the fourth day of the summer school. Today is dedicated to deep learning, and it's a great pleasure to introduce you to Lucy Wong. She is a postdoctoral investigator at the Allen Institute for Artificial Intelligence, AI2. You probably know the Semantic Scholar group and website. They have been making a lot of progress on trying to process text, figures, citations, all kinds of very interesting stuff. And she is an expert in text mining, ontologies, and natural language processing, especially for biomedical scientific text. So without further ado, let me introduce you to Lucy.
Thank you, Daniel. And it's a real pleasure for me to be here. Very excited to have a conversation with all of you. So as Daniel said, today I'll mostly be focusing on ways of applying NLP and deep learning to these problems around scientific text mining, and specifically on how to use these techniques to help you extract and synthesize knowledge from the literature, perhaps to answer a research question that you have. So I'm a researcher in the Semantic Scholar research group at the Allen Institute for AI, which is based out in Seattle, Washington. And Semantic Scholar, for those of you who aren't familiar, is sort of an academic search engine, but we also we try out and implement a lot of AI techniques to extract various types of knowledge from these papers and surface them to the public. So that's kind of our that's our main goal. And so let me just get started. So first of all, why do we care about scientific text mining? Of course, everyone knows here that there's tons of published papers each year, over 3 million science and engineering papers per year counted by the National Science Foundation. And this number continues to grow each year. And a large proportion of these papers, over a third, over 1 million per year, are biomedical papers. And this is sort of the subset of these papers that I care the most about. However, there's been some evidence done by other researchers that suggests that we've perhaps, as scholars and researchers, already hit this median reading ceiling of maybe around 250 to 300 papers per year. And what this means is it's just kind of the median number of papers that each of us is able to engage with each year in depth. And last year with COVID-19, we of course saw this phenomenon in action as well. Throughout 2020 and 2021, there were lots of headlines reporting this phenomenon of too many COVID-19 papers and this need for other tools to try to keep scientists afloat in the sea of new papers. And of course, in addition to the number of new papers, people also talk about problems around publishing low quality research, or maybe just kind of preliminary research that hasn't been fully validated. And there were also several notable high profile retractions during this year. So as someone who reads papers, maybe a researcher or clinician who's hitting these ceilings, you might be thinking, well, oh my goodness, there's so many papers. Which are the ones that I should be paying attention to? Which ones should I read? Or maybe you have those same questions about quality. So say you find a paper and it seems important, but it's still preprint and the sample size is small. So should you even trust the findings? And finally, you might ask, do the results in this paper even apply in my case? So as science of science researchers, a lot of these questions about quality and what the literature is collectively saying, they're also very relevant to our research questions. So taken together, these observations maybe emphasize the need for these automated and assistive NLP systems that can support these unique information seeking goals. So I'll just give a quick roadmap for what I plan on covering in the rest of this talk. So I'll start by going over this kind of current paradigm for applying natural language processing and deep learning to these problems of understanding scientific documents. So in this section, I'll give a quick primer on current NLP methods and language modeling. I know the audience is quite diverse, various levels of educational background. So some of you are more advanced in your careers than me. So this information may already be familiar to some of you. I'll then switch to discussing some content around scientific document representation, to how best to represent these documents to support these text mining and NLP applications. And then I'll go through a few examples of scientific NLP applications that I've worked on that can help illustrate how this current paradigm works in practice. So if you have any clarifying questions at any point, feel free to ask them during the talk, although Daniel also promised some discussion time at the end of the hour. So let's get started. First, how do we build systems that understand scientific text? So when approaching these problems, we generally think of systems that consist of a model or several models, this little text miner, that perform some task that we care about. So these models can take inputs in the form of text and then generate outputs in some form that we can interpret. So for example, you may be interested in extracting information from the input text, or maybe classifying it into certain groups and then aggregating the statistics of those classifications. So in science, the input documents are scientific documents. And in my case, I'm going to primarily focus on scientific papers. So these inputs can be paper abstracts. They can be sentences from these papers. They can consist of full text, some concatenation of a bunch of different documents, and whatever size of input text kind of makes sense for your problem. So here I'm showing an example sentence from the abstract of a paper on aducanumab, which is a kind of new Alzheimer's, potential Alzheimer's treatment medication. So for modeling, we have something that can learn the representation of this text that will help with our task. So since the topic of today is deep learning, I've visualized the deep neural network here. And it turns out that there are many such networks that are really good at learning representations of text. A deep neural network has an input layer that represents the input text in numbers. And then it has many hidden layers which capture features and interactions between these inputs. So for language, the input is this, it's this one-dimensional stream of tokens, a sequence of tokens. But we know that there are many complex interactions between any individual word with the other words in its surrounding context. So we gravitate towards network architectures that can help encode the text in a way that captures these relationships. It captures the syntax and semantics of this text. So recurrent neural networks, LSTMs, convolution neural networks, things that you're probably familiar with, all of these to some degree are network architectures that have historically been applied with success to modeling language. And currently, the most commonly used architecture is the transformer, which it uses an attention mechanism to weight and encode the relationships between these inputs. So then at the top of this network, we usually have some output layer. And the representation in this output layer is then something that we can cast into an output space based on the type of problem or the task that we're doing. So for example, if the goal is to classify text, we can cast the output representation to the classes 0 and 1 for binary classification using some sort of softmax or sigmoid activation function. And we may also want sequences as output. For example, we might want to label the part of speech of each word in the input text, that's pause tagging, or identify important named entities, which is NER. Or maybe just classify the tokens in the input sequence into a set of classes that we care about. So we can do this by decoding the output layer of this neural network into a set of tags in the output space. So for pause tagging, that would be parts of speech tags. For named entity recognition, maybe something like the entity types you care about, or these BIO or BILO tags. And perhaps you might want to generate new text. For example, you can also translate the input text into a different language or summarize or paraphrase it. So all of these tasks classification, sequence tagging, generation. These can all be done by decoding the representation of the text in the network into the output space the label space that you care about. And we learn the weights in this network using a supervision signal, which adjusts the weights by minimizing some defined loss function through gradient descent. So a paradigm that works really well for many types of language tasks is to pre-train a language model on a ton of unlabeled text using an objective like masked language modeling. What this means is that you take a bunch of natural text, and usually this text in this day and age is harvested from the internet, so it's web text. You mask out some percentage of it in the input, and then you train the language model to guess the masked words. This is called a closed task. So in this case, this input sequence is A, B, question mark, D, E, F, question mark, H. You train the model to guess what the question marks are supposed to be. So it turns out with the right architecture and enough unlabeled natural text, language model trained on this objective, it first, of course, becomes very good at guessing the masked words, but it also becomes quite good at doing all sorts of other language-related tasks, including classification, sequence tagging, the other tasks that I mentioned before. So one way to use this pre-trained language model is after training to freeze the model weights and then to use the language model's word representations directly for the end task. So this is pretty similar to getting something like pre-trained word embeddings of years past, things like word2vec or glove vectors, which some people might be familiar with. But when there's some more labeled data for the end task of interest, you can also fine-tune this pre-trained language model further. For example, you can add a few feed-forward layers on top of the output layer and learn the weights of those layers. Or you can backprop through some of the layers in the language model itself. So pre-training with different architectures in the language model and different objectives, it's led to the release of many of these pre-trained language models, some of which might be familiar, things like BERT and Roberta, or GPT-2 and GPT-3, which are more suitable for generating text. So in this paradigm of pre-training followed by fine-tuning to the end task, the pre-training part is much more expensive than fine-tuning, which means that people with more resources tend to pre-train these models and then release the frozen weights so that other people can end the architecture so people can work with them for their end tasks. So you can find a lot of these pre-trained models in various sizes in model zoos in places like Hugging Face. And of course, some of these models are also pre-trained on text from a specific domain. So these are called domain-adapted language models. For example, a language model that's been pre-trained on scientific text, something like SciBERT, or biomedical text, which gave us BioBERT, or clinical text, which gave us ClinBERT. So this is just a small sample of what's out there. And these language models, they've been pre-trained or they've seen much more of this text from a specific domain. And they're consequently better adapted to tasks in that specific domain. So very quickly, I just want to illustrate how these language models can be used for some specific classes of tasks. For example, for classification, the goal might be to map an input piece of text to a particular class. So something we might care about is, given a bunch of text about different drugs or medications, we might want to classify whether the text describes the medication as being effective or not effective. So this is the same example text as before. I've broken down this text into word tokens. And in the input, we also add this special token at the beginning, the CLS token, which based on some pre-training objectives is conditioned to try to capture information about the entire input text. So to perform the classification, we take these tokens, run them through the language model encoder, and then we take the CLS token representation output from the language model, add a few feed-forward layers on top, and then cast the output of these layers to either 0 or 1 using a softmax or other activation function. And we learn the weights of these additional layers based on the labeled data in our training corpus. Now we have a model that can perform this classification for new unseen instances, new sentences that we don't know about. And similarly for a sequence to sequence tag, for example, if you want to identify the tokens in the input corresponding to entity classes we talk about, like, for example, the drug or drugs or symptoms, we can also use an encoder-decoder architecture to achieve this. So now that we have this overall structure in place, I'll discuss some specific challenges around working with scientific documents. I'll talk more about how to formulate specific scientific NLP tasks. And very briefly, I'll touch a bit on how to evaluate the outputs of these models. So now I'm going to get more into the specifics. I don't know if there's any questions, but if you have them, feel free to jump in. So first of all, how do these scientific documents get converted into language model inputs? So most papers are not really in a form where we can readily use them. Most papers are in PDF. So we first need to make them machine readable so that we can provide some kind of suitable input into the language models I just discussed. So the problem with PDF is that it conflates layout and visual information with the semantic content of the document. So we need to first be able to identify the individual components in this paper. For example, the main body text, the figures and tables, and so on, to get at this information. Also, because these papers are sort of inherently multimodal, like they consist of text and images and math and all these other pieces, we have to determine what makes sense to keep around as the input into these models. So for this talk, I'm focusing on the text aspect. But just keep in mind that there's much more beyond just the text of scientific documents that might be useful. For example, a lot of results are in tables, so you might be interested in extracting the content of tables, or you might care about citation relationships, these are scattered throughout the text as inline citations, but they also are in these entries in the references section. So one of the first tasks we set out for ourselves when working with scientific documents is this need to extract the content of these papers and represent them, their structure and semantics. So for this, we propose to extract the content into JSON format, where various keys describe the metadata and data fields of these papers, and the values are the corresponding textual content for each of these keys. And we propose this representation in our 2020 ACL paper called Stork, in which we also release a data set of full text papers in this format, in this proposed format, to support scientific NLP and text mining. The question then becomes how to do this task. So one way is to take a purely text-based approach. We can use a PDF parser to extract all of the tokens from this PDF. As you can see, there's no structure to this token stream, maybe some new lines. And then we train a seek-to-seek model that classifies each individual token in this token stream to the corresponding class. And if we have some label data where we know all of the classes of these tokens, then we can use something like the language modeling approach I described before to train a model that does this. So a model trained in this way will tend to do fairly well. But as you can probably tell, it's throwing away a lot of information by converting the document into a flat token stream. So another approach is purely vision-based. So this problem can also be treated sort of like as a computer vision problem, essentially object detection and then classification of the text blocks on this page. And an architecture like the MASC RCNN framework is commonly used to do this. And when applied to this problem, it works reasonably well. But better than either of these approaches separately is to attempt to combine the textual and visual information together into one model. So Layout LM and Layout LM v2 published in ACL this year are models that try to do this. So Layout LM v2 uses not only tokens as input, this token embedding of the words, but also the location and size of the tokens on the page, the visual information. So by appending these information together and then feeding it as input into the language model can get much better at this token classification task. However, because the model requires changing the input format because it's appending this additional position embedding to the embedding of each token, this language model has to be pre-trained from scratch. So as I mentioned before, the pre-training part is actually the much more expensive part of this process. So it actually takes more than 1,200 GPU hours to train such a model from scratch. So we asked ourselves, can we do better? Or at least something that doesn't require training the language model from scratch. And we came up with a couple of ideas, one of which I'll show here. And the idea here is to inject positional information into the language model without altering the input format. So we have these token streams and token locations from the PDF parser. We also can use the vision approach to detect these text blocks. So we can simply insert special tokens at the boundaries of each of these blocks in the input token stream. So these are the special BLK tokens that you see here. These are the visual group indicator tokens. And these special tokens can help to indicate to a model, the language model, that the classification is more likely to change along these boundaries. So now when we feed this altered input token sequence into a pre-trained language model, we can provide the additional visual signal to the language model without altering the input representation. This is recent work led by one of our pre-doctoral researchers, Shannon Shen. The preprint is out on arXiv for those who are interested. So it turns out that inserting these special tokens at these block boundaries is very effective. We test out our hypothesis using 3 different BERT-based pre-trained language models, DistilBERT, BERT, and Layout LM. And injecting these special indicator tokens, it provides a significant boost in classification accuracy across the board for these models. So these are reported macro F1s on the GrowTope evaluation dataset, and this is a dataset published by another group that has 22 different token classes. And then because the input into the language model remains the same, so we're not changing the dimensions of the input representations by adding positions or other features, the model does not need to be retrained from scratch. So we're getting this boost in performance with a much smaller number of GPU hours than, for example, pre-training a layout LM from scratch. So we can take advantage of the pre-training that other people have already done. So what are the takeaways here? Again, keep in mind that scientific documents are inherently multimodal. So by choosing to work with text, we're actually throwing away a lot of information. And for some of the research questions that you care about, keeping other components of these documents around may be important. Also, after extracting content from PDFs, we have to do this token level classification to determine what's what. So I illustrated how to make use of textual and visual features to help improve classification accuracy. And of course, this comes without significant additional training costs. Now, once we have this higher accuracy, we can extract much higher quality data out of these PDFs, and the resulting data is less noisy and much more suitable for downstream text mining applications. And something I haven't mentioned before is that in addition to the research and modeling that we do, our group also provides a lot of data sets and resources to help support research on scientific NLP and scientific text mining. So these techniques that I'm describing here allow us to improve the quality of these community resources across the board. So now let me shift gears a bit to a few example applications. I'm going to walk through the formulation of 2 NLP tasks, how we develop the models to perform these tasks, how we acquired the training data, and then a bit more about how we evaluated the performance of our models. So first, I'll discuss the sup.ai project, where the goal was to extract evidence for supplement drug interactions from the literature. And this work was published in ACL 2020. And then I'll discuss a project on scientific fact-checking, where we are trying to understand how to fact-check scientific claims using the literature. This was also released in the EMNLP conference late last year. So to start, supplement drug interactions. Some quick motivation for this problem. There are a lot of people who take dietary supplements. These are things like vitamins, minerals, herbal medications. And these supplements have pharmacological effects, so they shouldn't be taken in combination with some meds. They interact negatively or sometimes positively. However, supplements are not heavily regulated. They're generally considered safe, and safety information can therefore be hard to find. But there's also many reports of these adverse interactions between supplements and medications. Here's just a couple of example papers. The FDA also collects many of these interactions as reports from individuals. So the question we asked ourselves was, can we identify some evidence for these supplement drug interactions from scientific papers at scale? That is, can we identify these sentences in the literature that provide evidence towards the interaction or lack of interaction between a pair of supplement and drug entities? So because this is kind of a binary classification problem at the core of it, this is the classification architecture I introduced in the earlier slides. So given that this binary classification task, it seems that we should be able to fairly easily plug these input texts right into this architecture. But in this case, there's also some considerations we need to tackle first. Which sentences should we try to classify? We can't classify them all. How do we prevent the model from memorizing pairs of entities that interact rather than learning how to identify interactions? And finally, where do we get the training data to learn the weights in this model? So first, which sentences should be classified? So here's a potential sentence that talks about the interaction between 3 supplements and 2 drugs. So to determine whether the sentence contains entities that we care about, we start by performing named entity recognition. So we use the SciSpacey library for this, and this is a kind of lightweight NLP library that's been trained to detect, it has a module that's been trained to detect biomedically relevant entities. So that gives us the underlined entities in this sentence. And to specifically identify entities that correspond to drugs and supplements, we use the SciSpacey linking module, entity linking module, to link these entities that were detected to entities in the Unified Medical Language System, or UMLS. This is a large consolidated knowledge base of biomedical entities that's maintained by the National Library of Medicine. And from the UMLS, we manually curate a set of entity identifiers that correspond to drugs and supplements. So after this linking, we're able to identify these, there's 3 supplements, those are the ones with green identifiers, and 2 drugs, which are the ones with pink identifiers in this sentence. So now we know which spans in our sentence correspond to supplements and drugs. So now that we have that information, it can help us figure out which of the sentences should be classified. So in Semantic Scholar, we have abstracts or full text from over 22 million biomedical papers. That's a lot of sentences, most of which probably don't contain what we're looking for. So if we classify them, we not only increase the cost of running our model, but we also increase the likelihood of more false positives. So we want to keep around only the promising candidates for classification. In this case, based on the results of entity linking, we can keep just the sentences that have at least 2 entities of the types that we care about, supplements or drugs. And this finally leaves us with about 33 million sentences from 4.6 million unique papers that potentially contain some kind of evidence towards an interaction. This is still a really large number, but it's much smaller than if we had just tried to process our whole corpus. So now, how do we indicate which entities we care about to the model, and then also prevent the model from memorizing these entities? So for example, this sentence talks about ginkgo biloba and both aspirin and warfarin. Those are drug entities. But maybe it's saying that an interaction exists between ginkgo and aspirin, but not ginkgo and warfarin, or vice versa, or some other combination. So we need to indicate to the model which are the potentially interacting entities where we're trying to detect this relationship. So in this case, say we're wondering about these yellow and pink entities. So the first thing we can do in the input token stream is we can delexicalize these entities of interest. So we replace them with these special tokens, ARC1 and ARC2. And not only does this indicate what entities we're caring about, it also has this kind of additional bonus factor of preventing the model from memorizing relationships between particular pairs of entities. So this is a technique that's often employed in relation classification, where you don't want the model to see too much about the entities themselves, but rather just the relationship around them. And that's what we're doing here. And finally, we ask, what training data? And because there's no labeled data on interactions between supplements and drugs, we actually borrow training data from a related task. It turns out that there are two training corpora for drug-drug interactions, the DDI 2013 corpus and the NLM DailyMed corpus. So both of these data sets, they contain a lot of sentences describing interactions between specified pairs of drug entities. I'm showing two example sentences here with different, it's actually the same sentence with different spans highlighted. And one of these variants has an interaction between the two underlined entities, and the other does not. So these sentences are pretty similar in form to those that are describing supplement interactions. So we believe that we can use the signal from these data sets to learn how to detect supplement interactions. So to train our network, we take the instances from these two data sets and we perform the same delexicalization of drug entities in the input text. So that the upper token stream is what we feed as input into the model. Then we train the network based on labels in these data sets. For the language model, we initialize our encoder from a Roberta large model, which is a BERT-based language model that's been it's had very strong performance on a variety of tasks. And after training, we call this model Roberta DDI. So again, we're using that same classification architecture. Now to put it all together during test time. Now that we have our trained classifier, that Roberta DDI, it's learned how to identify interactions, drug-drug interactions based on that labeled data from those two data sets. Now we've identified these 33 million candidate sentences from our corpus that potentially contain supplement interactions. So we take each candidate sentence at test time. We first delexicalize the entities, and then we run it through our trained language model to predict the class for that sentence. So how well does the model perform? So we evaluate first on the drug-drug interaction data sets that we trained on. And the performance of the model on these drug-drug interactions is quite high, in the kind of mid to high 80s F1. And these are precision, recall, and F1 scores computed on a held out test set, so something that the model's not seen before. And for supplement interactions, we don't have a test data, so we actually have to label one ourselves. We sample 500 candidate sentences, these supplement drug interaction sentences, to create a validation set independently. And we manually label these sentences for the occurrence of a supplement drug interaction. And in short, this model works fairly well for SDIs for detecting these supplement drug interactions. The precision is at least somewhat comparable to one of the drug-drug interaction data sets, but as you can see, the recall drops quite a bit, so the overall F1 is lower. So there's some room for improvement. And because we also created a public demo for this project, we performed some additional filtering of entities to try to increase the precision further. Because in this case, precision was a little bit more important than recall. And the research demo for sup.ai has been public for almost 2 years. It's still available online at sup.ai. And it currently sees around 20,000 users per month. And what this number signals to me is that there's a strong need for these types of systems that can help healthcare consumers discover health information that's more relevant to them. Because this is just a research prototype. And I think there's many ways to improve upon tools like these. So some quick takeaways for this project. When doing a classification task where there's kind of major class imbalance expected. Some candidate selection is necessary to reduce the false positives coming out of your model, and also usually to make the test data look more like your training data. And when labeled data is hard to find, which was the case in this project, you should consider whether transfer learning is an option. That's what we did here by training on the related task of identifying drug-drug interactions and then transferring the model over to the supplement drug interaction space. And another option is to use distance supervision to procure some sort of silver labeled data. Something we discussed but didn't do here is to extract supplement drug interaction relationships from knowledge bases and then use these to label sentences in the literature that mention these corresponding entities. That's a good way of generating silver labels at scale when it's too expensive to create gold supervision data. But of course, keep in mind that usually the signal in the silver labels is much weaker or sometimes too weak to actually learn from. So now we'll move on to the second application in fact-checking. So the main reason why we want to do science fact-checking is to try to manage or reduce misinformation in science. There's been a rapid proliferation of misinformation in the news and on the web. And last year, there were also numerous reports of kind of COVID-19 related public health misinformation. There have been fact-checking systems that have been deployed to some success in the news domain, but these systems do not work well for scientific claims for a few reasons. Scientific text tends to contain very specialized language, so it's out of domain for these models trained on news. Scientific claims also generally require some kind of background or expert knowledge in order to verify. And then also these claims are usually not clearly true or false. For example, when testing a new hypothesis, really the results are providing evidence towards the claim being true or not, and rather than saying it is true or not. So we ask, can we use the literature to fact check scientific claims? That is, starting with a claim like this, IL-6 signaling plays a major role in atherosclerotic cardiovascular disease. Can we identify evidence from the literature towards this claim, and then determine whether the evidence supports or refutes the claim? So back to this framework. The input now is a scientific claim, same one I showed before. And the output is both a classification of whether the claim is supported or refuted, similar to the binary classification of before, but we also now need the evidence that supports or refutes the claim. So to do this task, we need something different. First, because of this additional need for evidence, we need a retrieval module that can first take the claim as the input query and retrieve the corresponding papers or documents from the literature that might provide evidence towards this support or refutation decision. Then for each retrieved document, we can train a model that determines whether the document supports or refutes the claim. So for the input into this model, we first can concatenate the claim with the retrieved document. And then we can learn a classifier from the representation of that CLS token again. And we can also have another classifier at the same time that tells us whether each of the sentences within this retrieved document does or does not provide evidence towards that main support refutation classification. And we add these special SEP tokens between the sentences in the document to help learn the classifier from the representations of these SEP tokens in the encoder. So this is definitely a bit more complicated than the previous task we were doing in sub.ai. And in fact, we're asking the model to perform several tasks, right? Some at once, like the support refutation classification and the evidence not evidence classifications. And some of which, some components of this model also depend on the outputs of previous modules. For example, everything depends on the output of the retrieval module. But hopefully the overall structure is feeling familiar. Now for sub.ai, we used transfer learning to borrow from existing labeled data sets in an adjacent domain in order to train the model. But for this project, we didn't have something like that to leverage. So there's a few fact-checking data sets in the general domain. The most relevant of these are Fever, which is a really large data set of factoid claims from Wikipedia. And these are written and verified by crowd workers. And the other is UKP Snopes, which is like a similar political fact-checking data set. But what about claim verification in science? Well, when we first started working on this problem, there were no existing data sets in this domain. But there are some nice things about science and scientific texts that make this problem tractable. And one thing is that scientific papers are actually full of claims, these kind of citation relationships between papers. And the other is that in many cases, the claims, the citation relationship tells us where to look to find the evidence. However, because scientific text tends to be more technical in nature, it requires expert knowledge, we can't crowdsource data in this domain. So we have to rely on expert annotation. And that's what we did to create both a training and evaluation data set. So we hired and trained a group of skilled annotators to help us bridge these gaps and collect labeled training data. We start with these citation sentences, as I mentioned, extracted from these various papers. And we first asked the annotators to rewrite the citation sentence into claims. So here's an example. As you can see, the annotator performs significant simplification of the citation sentence, usually only taking one component of the sentence and casting it into an atomic claim. Then a different annotator will take this claim and one of the cited articles, those citation markers 44 and 45, and then identify the evidence from that article, if they exist, that support or refute this claim. There are a lot of annotators involved. We had 4 NLP researchers, 15 undergrads, and 5 graduate students with biomedical background who wrote claims and found evidence. And over the course of several months, these annotators wrote 1,400 claims and verified them against over 5,000 articles. And we released these claims and evidence as part of this SciFact data set in order to support other work in scientific fact-checking. And I stress that this annotation process was not easy. There was a lot of training and iteration that was necessary before we arrived at a reasonable agreement. But at the end of the day, we now have this data set that we can use to train the various components of this model. So for retrieval, we have the gold documents to be retrieved based on these citation relationships. And since we first released the dataset and tasks last year and created our baseline models, there have been many other groups that have worked on this problem with this dataset and have pushed this work forward. And the current best technique for retrieval is to combine BM25, which is a bag of words technique, using the claim as a query in the documents, the tokens in the document as what is to be retrieved. And combining this with a neural re-ranking method, for example, using T5. So this technique is used by Pradeep et al. In the Vertzerini model to very good effect. And for classification and identification of evidence, we found that the long former encoder works quite well. And we call this trained model the long checker. And something I didn't mention before is that language models like BERT or these other variants, they actually have limits on their input sequence length. And this is because transformer attention scales quadratically with input length, which makes it prohibitively expensive to process long sequences. In BERT, the limit of the input sequence is about 512 tokens, which is actually much shorter than a lot of our documents. And longformer and other architectures try to get around this problem by applying selective attention across these tokens. So for example, you might have windowed attention for each individual token to its neighboring tokens, but then global attention between all special tokens and all tokens. The special tokens are these things like the CLS or SEP tokens. So in this way, these models can process much longer sequences. So we apply longformer to our problem in order to both classify and identify evidence over the same output representation in one go. Very briefly, the model performs pretty well, achieving around 71 F1 on a held out test set when assessing both classification and evidence identification together. And this is better than previous high performing models. But as you can see, retrieval is still challenging. And we see this kind of 8-point drop in performance when switching from oracle retrieval, where we give the model the right documents, to using this trained retrieval module. I also want to touch very quickly on practical performance. I'm wrapping up fairly soon. So this Kaggle Cord-19 challenge happened at around the same time last year as we were working on this initial version of the system. And this challenge was a shared task on COVID-19 information extraction that I was involved in. We took the questions from that shared task. We asked several medical students to convert their answers into claims with the same instructions that we use for annotation. We then ran an earlier version of our model to get these kind of evidence sentences and the support refutation classifications. And then we asked the medical students, different medical students, to assess whether the results were plausible. Where plausible is defined as more than 50% of the retrieved evidence sentences have both the correct sentences identified and the right label. And this assessment yielded that about 2/3 of these were plausible. And you can kind of see these claims and the evidence in this kind of SciFact demo that we put up. And let me show you just an example of what this model is able to output. So given a claim like this one that talks about lopinavir or ritonavir, whether it's capable for treating coronavirus, the model is able to retrieve supported evidence like this one, which says that these drugs reduce coronavirus virus load significantly, which is, in fact, does support this claim. And it's also able to retrieve refutations like this one that says that the same drugs have been reported failed for curing SARS-CoV-2. And in fact, this can be adequately assessed as a refutation. So the quick takeaways, first, data annotation can be very expensive in domains like science. And though you can usually get away with using silver labels or distant supervision for training, having gold labeled data is usually necessary for evaluation. Another consideration is whether to model a complex task in a pipeline or end-to-end architecture. So a pipeline essentially breaks up the problem into many smaller modules where each one is maybe dependent on the previous module. And for example, in this case, we have that retrieval module, and then we have these other two subtasks of evidence extraction and support refutation classification. And sometimes it's easier to train models that do each of these subtasks individually and then glue these results together. But performance may be better when training a single model that can perform multiple steps, for example, with that long checker model. Other areas of improvement for this task, I already mentioned that retrieval is challenging and we can do better. We can also incorporate background knowledge. There's certain types of natural language reasoning that are still very hard for these models. For example, anything that involves numeracy or dealing with long-tailed named entities. And finally, we don't have a model that currently assesses the quality of the evidence or handles contradictory evidence. For example, in that last slide, there was contradictory evidence from two different papers. How should the reader weigh the evidence? Is one of the papers more trustworthy than the other? And these are ongoing questions that I'm interested in investigating. So in discussing these projects, I hope I've given folks a taste of how to formulate problems and models for scientific text mining. Coming back to these kind of main topics, let me briefly sum up some key takeaways. So regarding working with scientific documents, I just want to reiterate that these documents are multimodal and that by working with text, we're only working on a portion of these documents. And additionally, because we're extracting text out of PDFs, the resulting data can be quite noisy, especially compared to something like web text, which can affect the performance of these models. Regarding formulating and modeling scientific NLP tasks, in science, label training data tends to be sparse and expensive to create. So it's important to look to ways of acquiring silver labeled data, maybe through distant supervision or other data augmentation strategies, or exploiting transfer learning. And another thing to consider for more complex tasks is whether to construct separate models for each subtask or to try to train something end-to-end. And there's benefits and drawbacks to both. And finally, regarding evaluation, this is perhaps the most important place to expend expensive annotation resources. And it's also important to perform both quantitative and qualitative evaluation to really understand how a model is performing and whether it's making practically meaningful or useful predictions. Before I finish, here's just a list of resources I touched upon in this talk. You may find some of it useful in your own work. The first three, Semantic Scholar Corpus, Stork, and Core 19 are kind of data set resources. The first is focused on metadata, the latter two on full text. Stork doc to JSON is a library for converting scientific document types into the JSON format I discussed. And Vila, Sup.ai, and SciFact are the three individual projects that I presented during this talk. So happy text mining, and I'm happy to take any questions in the remaining time.
Thank you so much, Lucy. That was really amazing, and lots of very, very cool tasks. It seems like you have a lot of data and resources. I was looking at 1,800 hours of GPU. Are there any questions from the audience? There was a lot of discussion and paper sharing and lots of things happening in the chat.
Yes, absolutely, which I didn't get a chance to read.
Yeah, Zoom is not the best.
As I was talking, but if anyone would like to talk about anything in there.
So we've got a couple hands raised.
Oh, I don't see it. Oh, okay. So Hendrik, if you want to go, or I think this is the first one I see. So.
First of all, thanks for this very inspiring talk. I have a specific question because you mentioned, and that's basically very visible in a lot of the research literature, that right now transformer models are becoming basically the state of the art. So the question I have is that you said something that it's especially due to the attention mechanisms in these things. So what I'm interested in is why specifically do transformer models, which are like really huge and thus very computationally expensive to train, are becoming this kind of standard when there is, for instance, also the possibility to use attention heads for LSTM cells or the like. So the question would be like, is there some kind of heuristic you can use to choose, okay, here we do need a transformer model and here it suffices to, for instance, use an LSTM model?
Right. I think this is a really good question. And I think every time you approach a new problem, I don't think the default should be to pick up necessarily the state-of-the-art model immediately. I think sometimes the default should be to try shallow learning methods, try simpler models, kind of use those to test out your hypothesis and see if they're suitable for your problem first, because they tend to be much cheaper to implement in practice, and also can sometimes be easier to interpret what those models are doing. But I would say that this really comes down to, ultimately, like it comes down to what your constraints and needs are for your problem. Like, what are the resources available to you? What is the performance that you have to achieve? If you're answering a question, research question versus trying to deploy a system in practice, those needs are going to be very different. I think regarding architecture specifically, like transformer versus these other systems, something about transformer, I guess, is that you can train comparably larger models because of its parallelizability. So, you know, now that most people have put in the work to essentially pre-train these models, actually doing the fine tuning and the test time predictions is not that expensive. Like relatively, it's much cheaper. Again, I think it really depends on your both resource constraints and performance constraints of the problem. Not sure if that really answered your question, but there's a lot of parts to that decision.
Thank you, Lucy. So next, we have Fan with a question or with the hand raised.
Thanks. great talk. So I am seeking a bit more comments on, because you talked about the pipelining versus the end-to-end architectures, and I'm
Yeah.
interested in that part because it's something that, after you have done, then you got experience. It's not easy to be reading papers. So according to my understanding, so when you're saying pipelining, you mean kind of modular architecture of the the whole model pipeline, and then the end-to-end might be a cascade of models that just straight downward. I don't know if that's the understanding, and if you can give some, talk with the,
Sure.
in which case you use which architecture using the examples you just talked about, and what are the backs and advantages, things like that. Just more details. I want to hear.
Yeah, absolutely. I'll try to comment on two things. One is kind of what maybe the potential benefits and drawbacks are, and then I'll talk a bit about maybe how to pick. In terms of the differences between pipelining and end-to-end, I think you got it right. In pipelines, maybe you have, I think the last example with SciFact is a good example because it has those three components: that retrieval, evidence extraction, and classification task. So you can, in pipelining, you might just have a different BERT model for each of those tasks, and then you just glue the inputs together. So anything that comes out of the retrieval module necessarily constrains what kind of the second module, that evidence extraction, can do. And similarly, what comes out of that second module constrains what the third module will look like. So when you do this kind of pipelining approach, you always have kind of like a lossy pipeline. You're essentially like filtering out the data at each stage. But what it can help you do is kind of learn which parts of the pipeline are most challenging for your architecture, and you can kind of focus your attention to improving that. For example, if all of your loss is happening at retrieval, it's good to focus on improving that module, and you'll not necessarily, but you'll likely get performance gains through the rest of the modules. Whereas for something end-to-end, the overall performance might be better, because sometimes when you're trying to learn multiple tasks together, the model can benefit from each of the tasks. But interpreting which component is maybe the problem can be more challenging in that kind of architecture. And then in terms of determining which one to use, again, sometimes there's just actual hard constraints that prevent you from using a model in a certain way. So for example, in that last case where I was trying to do classification and evidence extraction at the same time. So you can't really do that using a BERT model very well, because the documents are usually longer than the token length cutoff that I mentioned. So something that you can do in pipelining is you can kind of do that evidence selection by appending the claim and each individual sentence, doing that classification, and then kind of concatenating the positive evidence sentences together to perform that final classification. So that's something where like before we had something like a long form or encoder decoder architecture, we just couldn't actually encode that whole sequence together to do these tasks at the same time. So, sometimes there's a hard constraint, and sometimes it's more about kind of ease of implementation or performance. Yeah.
Thanks.
Thank you. So we have a question. We have a question in the chat, but I think it was kind of answered by John. Basically, Lucy said that it's not that hard when you can transfer to other domains, so you don't need a lot of data, it seems. So we have a question from Sylvia. You have your hand raised.
Yes, I do. Yes, thanks. Yeah, I was wondering, and thank you so much for your talk. It was so interesting. I was wondering if you have a multilingual corpus, and if that is the case, if you have seen like any significant difference with your models. I mean, does it work the same if it's Chinese or Spanish or English? And yeah, that would be one question, and the other, if you happen to know anything similar as Villa, but for other types of text. I mean, like other types of documents, and yeah, that would be like thesis, which is my main concern. That would be cool. Thank you.
Sure. So for the first question regarding multilinguality, I wish I could say more, but it's true that our corpus specifically contains predominantly English language articles. And something, although it's not 100%, so we actually have quite a lot of papers in other languages, Arabic, Korean, Japanese, Spanish. These jump out to me as slightly larger portions of the corpus, but we don't have a good, I think we don't have a great multilingual science corpus, and something like that could be really beneficial. Another thing is that in science, I think multilingual corpuses are also maybe, I don't want to say more useful, but it'd also be nice to get kind of paired multilingual corpuses where we have the same article or abstract from these different languages. And I know that there are some publication venues that do have that. They have dual language abstracts. It's something that I'm certainly interested in the future. No one has created a resource like that, and we could probably all benefit from something like that. And in terms of like the modeling, there's been a lot of great successes in like multilingual language modeling. You can look into like multilingual BERT and things like that. Though, since they're not pre-trained on science, maybe kind of adapting them to this domain would make them work even better. And then your second question, can you remind me quickly what that was?
Oh, it was if you know about any projects like Villa, but for
yes.
other format.
Yeah, so in Villa, we primarily focus on scientific documents, but theoretically the framework can be applied to other PDF documents. You just need some kind of labeled data in that domain that tells you which classes you care about. But I would suggest you look into Layout LM. That's a much more general purpose kind of PDF like language vision classifier that might be able to help you with the documents that you're using.
Thank you.
All right, so maybe the last question, see if it's very quick. Rodri, maybe.
Yeah, I'll just very quick question. Yeah, thank you very much for the talk. It was fascinating. I just wondered if you knew of any papers or whether you have actually done this yourself that have used these methods to look at or to detect citation bias or citation distortion, where the meaning of a study is kind of subverted through the literature. Or as a sociologist, there's also another very interesting case of where the same study is interpreted in dramatically different ways. I just, that's my kind of research area. So yeah, I got very excited when you showed me the kind of different interpretations of the same evidence.
Yeah, this is a really, really fascinating questions in that area. I don't know about anything super direct, but I can think of, there's a recent paper from Isabel Augenstein and Dustin Wright that look at kind of when claims made in scientific articles get translated into maybe claims made in the news media, and whether hedging is removed. Like there's, what kinds of transformations occur when you move from that domain, essentially science to news. And I think we've definitely had discussions around when people cite other papers, do you also make the same kinds of adjustments to those claims? Like, do you also get rid of these like hedging words or modifiers and just take the kind of like the core of the claim? We've done some work. Our group has done quite a bit of work on citation intent classification. So this is when you take all these citations and try to determine what the intent of that citation relationship is. So you can look into, there's two papers, one that's from 2 years ago I can send these in the chat afterwards. I think that'll be a little bit easier than talking about that.
Excellent. Well, thank you very much. That would be brilliant.
Yeah, thank you so much, Lucy. It was fascinating talk and very, very exciting to see all this progress in NLP and being actually implemented in a real search engine. So with that, I would like to give a round of applause and then click my reaction here on Zoom. So thank you so much.
Thank you. Thank you all.